Hi, today we're going to talk about infrared spectroscopy, which is a great tool in determining molecular structure. So before we understand how to use IR in the lab, we first need to look at what's happening on the molecular level. Let's go back to the electromagnetic spectrum. Remember that the shorter the wavelength, the higher the energy radiation you get. And the longer the wavelength, the lower the energy. Before now, we were mostly looking at spectroscopy that used the ultraviolet and visible parts of the spectrum, and we talked about how photons in this area of the spectrum move electrons from lower energy levels to higher energy levels. So what happens when we hit a molecule with infrared radiation? You could see that IR is lower energy than ultraviolet or visible light. As a result, it doesn't have enough energy to move electrons to higher energy levels. Instead, it causes vibrations within a molecule. Now, what do I mean by that? When you talked about bond lengths back in general chemistry, you might have seen a graph like this. Here we have internuclear distance on the x-axis and energy on the y-axis. You could see that if two nuclei are close together, that will be a very high energy state because you have two positively charged particles close to each other. And as the nuclei move farther away, the energy of the system decreases. But remember, this is looking at the energy between two bonded atoms that are held together by electrostatic attraction between the nuclei and the electrons. So if you pull the nuclei too far apart, you go to a higher energy state where the electrons want to pull the nuclei back together. Of course, at some point, the atoms are far enough apart that they can no longer share electrons. The bond is broken, and you no longer have an increase in energy as you continue to separate the atoms. When we think about bond length, we normally talk about this distance right here where the energy is at a minimum. If you think of this as an energy hill, you can imagine that a ball would always roll to the bottom. If you put energy into the ball, that would allow you to push that ball up one side or another of the hill, but the ball wouldn't stay there. As soon as you let go, it would roll down to the bottom. But then, because of its momentum, it would roll up the other side a little bit, and then down, and then up, and so on and so on. In other words, if you put a little energy into a bond, your internuclear distance may change by going back and forth, shorter and longer, and shorter and longer, and so on. And that's one way to get vibration in your molecule. Now, you could make a similar graph with bond angles. If you have a small enough bond angle, you would end up with atoms very close to each other, and that would be a high energy state, because they would repel. You would get the lowest energy when all of the atoms are equally spaced from each other. But again, you can put energy in and push them together, and then they would move away from each other and back and forth. So one way to model these vibrations is by treating the nuclei like weights attached to a spring. Now, if you think about your experience with springs, you know that some are easier to bend than others. How much a system like this vibrates will depend on the stiffness of the spring. A stiff spring will vibrate slowly, while a less stiff spring will vibrate more quickly. And then, of course, the masses of the weights attached to the spring also matter. Now, I'm not going to get into this very deeply. That's something that gets done in physical chemistry, but it helps you to envision what's going on if you think about the spring model. What's actually holding these two nuclei together are the bonding electrons, and so those would represent our spring. And you can imagine that a double bond would hold more closely than a single bond. You can also imagine that a polar bond would hold differently than a nonpolar bond. The nuclei then will be our weights, and you can imagine that nuclei of different masses and different charges would behave differently in our system. When we hit a molecule with infrared light, we see two categories of vibrations. First, bending, which is a change in a bond angle somewhere in that molecule. And second, stretching, which is a change in bond length. Let's now look at different sorts of vibrations within these categories. I'm going to model a molecule undergoing these different vibrations. You're going to have to use your imagination a little bit. So I have a hydrogen atom on each of my hands and a carbon atom on my chest. You can't see it, but pretend I have another carbon atom further down my body. And of course, you're going to have to pretend my head is not there and my arms are bonds. Now, unfortunately, my arms are not infinitely flexible or stretchable, so pay closer attention to the position of the atoms than to my actual arms. So first I'm going to model bending, which if you remember is a change in bond angles. We split the different bending vibrations into two types, in plane and out of plane. With in plane bending, you can see that all of the atoms remain flat relative to each other. So our first type of in plane bending is what we call scissoring, in which atoms move away from and then towards each other. Next we have rocking, in which the atoms are both moving in the same direction. Now remember, there is another carbon further down my body, so these hydrogens are changing position with respect to that carbon. Okay, now let's look at out of plane bending. First, we have wagging. It's obvious why this is an out of plane bend, because you can actually see the hydrogens moving towards you. Twisting is a little different from wagging because you have one hydrogen moving forward while the other one moves back. Let's move on to stretching, which again is a change in bond length. We have two sorts of stretching. Symmetrical, which means that both bonds get longer or shorter at the same time, or asymmetrical, where one bond gets longer while the other gets shorter. Now that you understand what is happening at the molecular level, let's look at an infrared spectrum. This particular spectrum is for phenol. I put its structure down below. On the y-axis of the graph is the transmittance. Remember that a transmittance value of 1 means that 100% of the light is getting through, that's what we see at the top, and that none of it is absorbed. Likewise, a transmittance value of 0, which you see on the bottom, means that none of the light is getting through, it's all being absorbed. In other words, these very large dips in our spectrum, like this one here, are absorption peaks. Now on the x-axis, we have this thing called a wave number. What is that? If you think back to the definition of frequency, you remember that it is the number of waves within a set time period. So wave number is kind of like that, but it refers to the number of waves in a given distance. Basically, it's the inverse of wavelength. So the longer the wavelength, the smaller the wave number, and the lower the energy. Okay, back to the spectrum of phenol. Look at this section right here, inside the purple box. How many peaks do you see? I see 5. One here, this big one right here, the third one here, and then these two little peaks right here. One of the things you really notice when you're looking at an IR spectrum is that you have a lot of overlapping peaks. You can imagine what it would be like if we separated these into different peaks, but each of those peaks represents a different vibration. So you can also see a difference in the sorts of peaks we have, not just where they're located on the spectrum, but in how deep they go and how wide they are. When we're evaluating peaks, we often talk about the width as being broad, like this one here, or narrow, like that one. We also talk about the strength of a peak, strong, medium, or weak. A weak peak is something that doesn't absorb much infrared light and therefore does not get close to the bottom of the spectrum. A strong peak absorbs most of the infrared light and therefore goes near the bottom of the spectrum, and a medium peak is in between those options. The strength and width of a peak depends on what sorts of bonds you have and what atoms those bonds are connecting. And you can't just guess, you have to learn what is what. So this awesome graphic by Compound Interest summarizes many of the peaks you can find on an infrared spectrum and what sort of bonds they correspond to. I'm going to drop a link to the original graphic down below in the description. I definitely encourage you to pause the video, download the graphic, and then look at it as we view our next spectrum. So this next spectrum is for eugenol, one of the compounds that gives cloves their distinctive smell. This graphic shows both the structure and the systemic name for allyl 2-methoxyphenol. Let me walk you through some of the peaks that we see on the spectrum. First, we have this broad peak, which tells you that you have to have an alcohol or OH group. Next, we have this set of overlapping peaks. Very likely the peaks on this side correspond to the aromatic portion, while the peak on this side corresponds to this double bond down here. Now this double peak over on this side also represents those same sorts of bonds. And finally, I'm pretty sure that this peak right here, which is pretty strong compared to most of the other overlapping peaks in the area, is for the ester. Now, as you can see, the area here between 500 and 1500 is a real mess of overlapping peaks. That's the case for most organic compounds. So we call that area the fingerprint region, because since each compound has many peaks in that area that all overlap in a unique way, we can use it to identify them. Now I'm going to show you one last spectrum, this one for water. You can see that this spectrum looks very different from the last two we saw. Where the others had a lot of overlapping peaks in the fingerprint region, water has a very strong absorbance. Water also completely absorbs most infrared light in this 3000 to 3500 range. In other words, water is a really bad thing to do infrared spectroscopy on. From a practical standpoint, this means we can't do IR spectroscopy on aqueous solutions because the water will absorb all IR. In fact, we can only use solvents and sample plates that are transparent to infrared radiation. So IR sample prep can be a real pain. Samples are generally mounted on or in some sort of salt, generally potassium bromide. How do you do that? Well, one way is to dissolve your substance in carbon tetrachloride, which doesn't absorb infrared in the wavelengths we look at, and then drop the solution directly onto a salt plate made of KBr, and then put another salt plate on top, and then put that little sandwich of salt plates in the instrument to read. Now, carbon tetrachloride is a nonpolar substance, so it doesn't dissolve the salt, but it also means some things may not dissolve in it. If that's the case, you can dissolve your analyte in a solvent like acetone, drop that on the salt plate, and then let it dry. Because acetone vaporizes very quickly, there should be none left when you do your analysis. Finally, if you have a pure solid, you can grind it into a fine powder, mix it with crystalline potassium bromide, and then put it in the press to form a hard pellet. The pellet method is unique in that you don't have to put your sample on a salt plate because you've essentially made it into a salt plate that also contains your substance. So now let's look at the inside of two sorts of infrared spectrometers. The first is what we call dispersive infrared spectroscopy, which you might think of as regular infrared. This really isn't a whole lot different than UV vis spectroscopy, other than the wavelength of radiation is different. So you see, we start with an IR source. Then there are a bunch of curved or angled mirrors. The light leaves the source, bounces off the mirrors, and through the reference cell. It hits this special mirror called a chopper before going in to be analyzed. So why does it take such a circuitous route? Because this is one of the instruments where we actually use a reference cell instead of a blank. So there's a second set of mirrors which directs another light beam through the sample cell. The chopper is a special one-way mirror that reflects the light coming from the reference cell, but allows light from the sample cell to pass through. So once the light gets past the chopper, whether it's coming from the reference or the sample path, it takes the same route. First, it goes to the monochromator, where the wavelength is selected, and then it enters the detector. Now let's talk about Fourier transform infrared spectroscopy, or FTIR. In order to understand how FTIR is different from dispersive IR spectroscopy, you need to understand constructive and destructive interference of light waves. If you think about adding two waves that are offset by half a wavelength, so one hits a peak while the other hits a trough, you'll see that these waves are going to add to zero. They will cancel each other out. But what happens if instead you try combining the waves where the peaks and the troughs are lined up with each other? You basically end up with a wave where the peaks are twice as high and the troughs twice as low. Things get a bit more complicated when you combine waves of slightly different wavelengths. By combining multiple waves offset in just the right way and with the correct combination of wavelengths, you can send pulses of light. And it is these pulses of light that we use to analyze samples in FTIR. So how does an FTIR spectrometer differ from a dispersive spectrometer? First of all, it may have more than one light source with a series of mirrors that allows these beams of different wavelengths to overlap. Secondly, there will be multiple mirrors, some fixed so the light is always traveling the same distance, but at least one movable mirror that can adjust the distance the light has to travel so that you can get light waves traveling different distances. This thing you see that they call the beam splitter is basically a mirrored prism that reflects some light and allows the rest to pass through. All of the optics in the first part of the instrument allow the light waves to combine to form the pulses of infrared that are required. So why use this complicated setup? First of all, FTIR allows us to use what we call far infrared, the longer wavelengths that correspond to 10 to 200 inverse centimeters. Dispersive IR can't get past 200 inverse centimeters. Secondly, FTIR is faster than dispersive IR. In the same amount of time it takes a dispersive IR to measure one spectrum, FTIR can take several spectra and average them to get a less noisy signal. And FTIR just gives us better readings overall. We can get better resolution of wavelengths, and we lose less energy on the way to the detector, so our signal is stronger. In a nutshell, infrared spectroscopy allows us to analyze molecular structure. We can use it in the lab, where it's generally used to analyze complex organic molecules, or we could use it in remote sensing, where we can analyze both organic and mineral components. I hope this was helpful, and I look forward to seeing you again soon.